This is video 1 for chapter 12 in unit 4, talking about specifically sound waves. In this video, we'll talk about absolute sound intensity, as well as power and radius from circular spheres that you will be making. Obviously, sound travels in all directions, so that's why we're going to talk about the radius, not the distance between sources. Once again, circular spheres is what you're going to make. Okay, so to start off here with your vocab, we want to talk about the idea that sound waves are longitudinal waves. In other words, that means that the particles are traveling parallel to the direction of motion. So those particles are being compressed and then squeezed out, stretched out, in lack of a better term. So you're going to have areas of compression and rarefaction. The areas of compression, you're going to see high pressure, and those are going to be known as your crests on your sine wave. Whereas rarefaction is areas of low pressure, and they are going to be known as your troughs on your sine wave. So right here would be a crest, and you can see that that does coordinate with areas of compression. So let's also add that those are dark fringes. You'll be able to understand the idea of fringes or bands later on. Whereas down here, below the equilibrium line, down here would be a trough. And troughs are going to be light fringes. So you have made your sine wave from your longitudinal wave, noting that areas of compression are related to crests and areas of rarefaction are related to troughs. So once again, the sound waves are longitudinal. In which direction, excuse me, it's a question to pose. Which direction are vibrations headed in comparison to the direction of motion? We told you this on the previous slide. This is parallel. Particles vibrate parallel to the direction of motion. So if we want to label this, just kind of think of where you want to move this. Where do you want to move the word compression? Areas of compression are going to be right here, for instance. Let me rotate that a little bit. So that would be an area of compression. How about an area of low pressure? An area of low pressure. Our low pressure is going to be related to crests or to troughs. They're going to be related to troughs. I'm going to actually put this guy right here just so that he is not taking up too much space on our waves here. In comparison, high pressure would then be related to a crest. So let's put him right there because that's an area of a crest. A trough is obviously going to go down here on our sine wave. A crest will go down here on our sine wave. And areas of rarefaction are going to go up here, and that is going to be like the white areas, the light bands. So please make sure you understand the difference between a longitudinal wave and a sine wave on these slides. Hearing the sound waves. So audible sound waves. What I'd like you to jot down here is sound waves that the average human ear can hear. Sound waves that the average human ear can hear. This audible range goes from 20 to 20,000 hertz. So it's a frequency that we're looking at here. This should make sense. Infra, that means before. Sonic is sound. So sounds that you can hear prior to 20 are going to be known as infrasonic sound waves. So for infrasonic sound waves, less than 20 hertz. To be a little bit more specific, guys, sounds that are registering at less than 20 hertz. Ultra is after. Think about like infrared versus ultraviolet. That should make sense from Roy G. Biv, how you have Roy G. Biv. And prior to that is infrared, ultraviolet. So common sense for your electromagnetic spectrum there. It means the same exact thing, except for talking about light, which is chapter 13. In chapter 12, we're talking about sound waves. So ultrasonic waves are going to be waves that are, think about this quantity here. Ultrasonic are going to be waves that are registering at more than 20,000 hertz. So whispering, for instance, would obviously be infra. Okay, pitch. Definition here, measure of how high or low a sound is perceived to be. It is a measure of how high or low a sound is perceived to be. You're going to be thinking about frequency when you're talking about pitch. A high frequency is a high pitch. So from this, I'm going to say that it is determined by frequency. Frequency is going to determine what your pitch is. So in other words, as frequency increases, pitch is going to, we'll stop and think about it. Frequency and pitch are directly related to each other. This isn't really like an equation, guys. So I guess more appropriately, you would say that they are proportional to each other. But long story short, frequency increases, pitch increases. So an opera singer singing those high notes. Speed of sound depends on the medium. Speed of sound depends on the medium. So we're talking about mechanical waves. Well, if we're talking about mechanical waves, that means that sound waves do require a medium because longitudinal waves are mechanical waves. Okay, although sound waves can travel through solids, liquids, and gases, they're going to travel the best through gases. Okay, so with this, you know that it's going to be the gases because those are going to be like areas where the molecules, particles, let's just be very general here, atoms, the particles have a lot of area to spread out. So a lot of area. You're not as compressed, all just constantly having collisions like what solids are. Gases can spread out, they can be heard much further away, etc., etc. So particles have a lot of space. Think about what you know about solids, liquids, and volume, or solids, liquids, and gases. They have defined space or defined area, unlike gases, they do not. Okay, so when does sound travel faster in gases? Please make sure you watch these two videos. I'm not going to take time right now in your video lesson here to click on them. The sonic boom is pretty cool. It shows exactly how the waves, how we have clouds, like the sky's blue, but whenever there's quote-unquote clouds, there's white. Well, what's happening? Those air molecules are compressing together. When those air molecules compress together, they become white because of the refraction of the light. That's chapter 14 that we'll be talking about. Rubin's tube is a pretty sweet experiment that the gentleman on Mythbusters did, which deals with fire and gas and stuff. So we're not going to build one, but it's a really neat experiment where you can very clearly see sounding waves and how sound does need a medium, gas in that case, air, to travel through. So please do make sure after this is over, you click at least at the bare minimum on Rubin's tube, but the sonic boom definitely, I think, brings it home for those of us that are visual learners. Please make sure you watch both of those guys. Okay, sound waves travel away from a vibrating source in all three dimensions, X, Y, and Z. When I'm standing in front of you during class, although my voice may be projected straight ahead, everyone around me can hear my voice, right? So sound travels in 3D motion. The big thing that I want you to get here is that the further you zoom in on this, the more parallel these rays are going to seem to become. And then the distance between them is going to be pretty equidistant to each other. Okay? Please keep that in mind. So in other words, what's this kind of look like? It kind of looks like a bullseye, right? So that's what I want you to be thinking about with this. Here's our source. It's like the money right there, and you're going to radiate out in all directions. So this is say up, down, forward, backwards, left, right, etc., etc. If you would, like this is you looking at waves that were generated standing on top of that lake, but if you were in the water and you were able to like just put your eyes right at water level and you saw these waves crashing towards your eyes, you would see this picture right here. So you'd be able to see that these waves are making areas of compressions and rarefactions. Okay, Doppler effect. For the Doppler effect, what we're looking at is an observed change in frequency where there is relative motion between the source of waves and an observer. So look at observer A right here. These waves, the space between them, the wavelength, in other words, is what we're measuring there, seems to definitely be less for observer A than it is for observer B's wavelength. So for observer A, you're seeing that the waves are being compressed to each other, so it has a smaller wavelength, thus higher frequency, as velocity is your constant. So to appropriately apply Doppler effect, we have to think about velocity equals frequency times wavelength, okay? Whereas over here, you're going to have larger, longer wavelength, therefore you're going to have lower frequency, but once again, but once again, your velocity is going to be constant throughout this system. This person is standing still. This person is standing still. So it's like the waves are smacking you, right? They're hitting you. So as that sound source is getting closer and closer to you, as you are stationary, you're squeezing, you're compressing all those waves, therefore creating a higher pressure. A higher pressure, higher crests, means a higher frequency, shorter wavelengths. When the Doppler effect can occur, we can also look at it whenever there is relative motion between the source of waves and observer. Whenever there is relative motion, that's the movement. So right here is relative motion between observer and I'm just going to call it sound source. So another thing that we're used to seeing like every day is Doppler effect, which like Doppler radar for weather and whatnot. That'd be another place where you would see this. How far away is that weather from us? How can they incorporate that? So the next thing we want to look at is intensity, in which intensity is the rate at which energy flows through a unit area perpendicular to the direction of wave motion. So intensity does not have any abbreviations. You have to write out the word intensity, and that is going to be watts per meter squared. Therefore, the equation is intensity equals 4 pi r squared. Power, I apologize, erase that, guys. It is power over 4 pi r squared. Power is measured in watts, and radius has to be measured in meters. Therefore, intensity is watts per meters squared. Okay, watts per meters squared. From your sample problem, use your intensity to get 0.20 divided by 4 pi, 3.2 squared. Okay, so filling this in, you're going to see that your intensity will give you 1.6 times 10 to the negative third. You want 2 sig figs, so 1.6 times 10 to the negative third watts per meter squared. Here are your correct answers to practice A problems.